All right, so in this episode, I will be discussing the paper called Achieving Energetic Superiority Through System-Level Quantum Circuit Simulation. Go ahead and check out the description for the authors and the affiliated institutions. Some of the science, kind of the background I covered in my podcast, Science in Perspective. So I'll give you a little bit of the background of kind of the motivation behind this research paper, and then we'll dive right into the different figures and talk about what's happening. So in 2019, Google made an announcement that they had achieved quantum supremacy. The idea behind quantum supremacy is that you can showcase that a quantum computer can do a calculation that a classical computer cannot. Classical computer, of course, being the ones that you and I use on our smartphones, desktop, laptops. So they made this announcement in 2019 for a kind of this sampling problem that apparently only a quantum computer would really be able to do. They said that it would take a classical computer 10,000 plus years to do it. And here we are only 4 or 5 years later, 2024, this paper comes out and shows that classical computing can actually do the same computation. Of course, it's a very beefed up version of, supercomputing, if you will. The classical computer, the amount of memory and GPUs that were thrown at it, as we will see, were massive. A lot of optimizations had to take place, as we will see with this parallel scheme that the authors came up with and all that. But the point is that classical computing can indeed do the type of quantum calculations, at least in this situation, that apparently quantum computers were only supposed to do. So this paper, is basically challenging Google's claim that quantum computers, or specifically their Sycamore quantum computer, can do something that no classical computer could do or would take 10,000 years, right? Here we are 4 or 5 years later and they did it. Okay, so let's jump into the paper. Let's understand the science deeply. Again, if you want some of that kind of background story and some of the main scientific concepts, go check out the Science in Perspective episode, episode 1. But for the more kind of technically minded and ones who really want to get into the details of the science itself, this is the episode to listen to. So in figure 1, what we're looking at here is the difference between classical and quantum computers in terms of performance. You can see the kind of shaded rose-colored rectangle in the bottom left showing the performance across essentially different computing approaches. You've got the Sycamore computer from Google not performing as well as these authors' approach, which is their tensor network. They have a variety of setups for their tensor networks to compute the same problem classically. And, again, in the later figures, we'll talk about how they're doing this. But just briefly, a tensor network, whenever you're dealing with very complex problems that you have to solve on a computer, tensors are often a way to go. They're also quite common in trying to model quantum systems, specifically tensor networks. So a tensor network is you take tensors, which are, of course, just a generalization of the matrix beyond the 2 dimensions, right? So take a matrix and go 3, 4, 5 to many dimensions. You're using a tensor, so it captures high dimensionality. And the tensor network is literally just a network of tensors, where the nodes are going to be the tensors themselves and the edges are going to be the communication between the tensors. So when you want to simulate something like a quantum system, it makes sense to use something like a tensor network because you can kind of, quote unquote, collapse the tensor network. It's actually called a contraction. And it's somewhat analogous to what you might do if you try to collapse a quantum system down to its answer, right? A real physical quantum system, let's say that's happening inside a quantum computer, would be composed of qubits. Those qubits would have superposition and entanglement. You would have the quantum gate acting on those qubits so that they would perform the kind of entanglement and superposition needed to get the calculation to occur. And you would essentially, similar to, essentially like a wave function, collapse that wave function down to its final kind of most probable answer. So you can essentially simulate that, if you will, using a tensor network. You capture the high dimensionality through tensors as opposed to some physical quantum system, and you, quote unquote, collapse that tensor network down by using contraction, which is essentially just the linear algebra that you're doing on those tensors to pare them down to the one or very few tensors that would represent the answer. So that's what a tensor network is, and that's what they're going to use in this paper to simulate the quantum system, the quantum circuit, essentially kind of reproduce what Sycamore is doing, but on a classical computer, and show that the classical computer can indeed run the calculation. So figure 1 is showing that in terms of performance, the classical computing approach is beating the quantum computer, despite Google's claim that, a classical computer would take 10,000 years to achieve the same result. So it's obviously pretty impressive. So let's dive a little bit more into it to see how this occurs. In figure 2, we're looking at the trade-off between the space complexity and time complexity. This is a common thing in computing. Here we have, it's a trade-off because if you throw more memory at the computation, so the more, higher space complexity, then, the time complexity can come down because you're giving more space to the problem. So if that's good, you want time complexity to come down, but now your memory footprint is huge, right? You have too much memory. So chances are you can't just throw, an infinite amount of memory at the problem, obviously, because you only have so many resources. And if you want that space complexity to come down, you could, the inverse relationship is going to push the time complexity to the max, and you don't have forever, like the 10,000 years, to wait to solve the problem. So what the authors are doing here is trying to find the optimal kind of area or location between the space complexity and time complexity. They have to look at the resources that they have available to do the computation and then try to design an algorithm accordingly. So in that top part of figure 2, you see, essentially the curve that traces out the trade-off between that space-time complexity. They're looking for the optimal solution given the resources they have. And in the bottom part, you're taking a look at the time complexity distributions. So you're just taking a look at the distribution, of the performance given the time complexity. And again, just trying to find where that optimal value is. So between the top and bottom parts of this chart in figure 2, they can get a sense of how to design the algorithm. And that's going to be true for a lot of the figures we discuss going forward, as they're trying to get into the nature of the problem and the computation and understand the space-time complexity and figure out how to design the best possible algorithm, because that's going to make things comparable. In figure 1, I just want to be clear that if we just go back to that, the solid circles are classical and the rectangles are quantum, and they also have these hollow circles, and that just represents a classical loophole. What that means is in classical computing, you can end up doing the sampling that you do from the quantum circuit in kind of an artificial way. And what that means is you end up getting correlations in the sampling, which you're not supposed to get. The reason that's a problem, and they're calling it a loophole, is because if you sample with correlations, it artificially inflates the performance of the classical computer. And now you're not getting a fair comparison between the classical and quantum computation, which of course you want to do. You want that to be a fair comparison if you're going to say that classical computing is better. So that's what that loophole is. So I went back to figure 1 there because now back to figure 2, again, we want to have a really good performing classical algorithm so that we can accurately compare it to something like the perfect thing, which might be the quantum computer, right? Perfect in the sense that it's an actual quantum system doing a quantum thing. So you want the comparison to be really good and then see if you can beef up the classical system to actually perform better than the quantum. This figure 2 is also in relation to the tensor contractions. Again, I talked about that at the beginning. So you're basically exploring a possibility space of different possible contraction pathways. So think of a contraction pathway as essentially, almost like a linear algebra recipe you would take to contract your tensors down to an answer. And there's a bunch that you could take, but only a few of those are going to be worthwhile because they're more efficient. So you could take a contraction pathway that is very inefficient, which most of them will be, if they work at all. And it would just take too long to contract your tensor network down to the answer. But a few of them in that space of possibilities are going to be relatively efficient. Okay, so again, these authors are running these classical computations on these tensor networks. They need to contract them down to the answer, and they have to do that as effectively and efficiently as possible. Otherwise, this isn't a good comparison to quantum computing, if that makes sense. And they're just not going to beat the quantum computer unless you have a contraction pathway that is pretty efficient. Okay, so space-time complexity trade-offs with respect to contraction pathways, trying to find that optimal part. And then we get into figure 3. And in figure 3, we are looking at a 5-qubit system. So what they're doing here is they're essentially saying, look, the Google Sycamore quantum computer in reality has, let's say, 50 plus qubits. We think we can essentially simulate it kind of using a model of a 5-qubit system. And so they're really just kind of elucidating what the quantum circuit looks like as a model. And they highlight the 1-qubit gate and the 2-qubit gates, quantum gates. These quantum gates are acting on the qubits so that they essentially kind of align themselves to what they're supposed to be doing physically to have superposition and entanglement. So for example, a 2-qubit gate would act on 2 qubits and kind of help enforce something like a superposition or an entanglement between them, which is, again, the physical state these qubits need to be in order for them to do the calculation they're supposed to do, because that's the point of quantum computing, is to take advantage of superposition and entanglement to actually run the calculations, right? And again, if you want some more of the kind of conceptual background of how superposition and entanglement allow calculations to occur, I cover this in my first Science in Perspective episode. So go ahead and check that out. I'll put the link in the description. So they're showing the model of the circuit, and they kind of take a subset of it and show kind of the sequence of operations. Again, they're trying to show that if they're going to build a tensor network that does what a quantum circuit does in reality, they need to model that correctly. They need to know that their tensor network is a good, kind of replica or simulation of the sequence of steps that you would expect to take place in a quantum circuit. And of course, that's what they then have to optimize and scale to compute this better than the quantum computer does. So it's just kind of a view of what that model of a quantum circuit looks like. Now in figure 4, you are dealing with the actual kind of architecture of what they call this kind of 3-tier parallelism or parallelizing scheme. Okay, so the 3-tier parallelism scheme is how they're breaking the problem apart into its pieces. And this is obviously critical. So, you might normally do a tensor network, let's say on one node, but that's not going to cut it. It's not enough computational power to beat the quantum computer. So they're going to scale this tensor network, beyond a single node. And there was a cost to doing that, because now you've got this inter-node communication that you're going to have to deal with. That's always the cost when you go to kind of do something distributed and in parallel. So on the left, they're kind of showing the breakdown from kind of the global top level and then how that trickles down right down to the device level. In A and in B, they're, kind of getting into how the internode and internode communication is actually happening. The internode is going to be done using the InfiniBand, okay, as a way to get that communication as broadband and as fast as possible. And then the intranode communication, they're going after that right at the device level, and they're going to use the NVLink to do that. So it's basically just their they break it down as a hierarchy, this 3-tier parallelism, and it's how they can distribute something like a tensor network. And they're showing that they're going right to the device level to control, the speed of communication, right? Intranode communication with that NVLink, internode communication with the InfiniBand. They got to have the bandwidth there. They got to have the communication there, because they know that's a big trade-off to scaling. Okay, so that's just outlining how they approach that. And in figure 5, what you're dealing with here is the difference between kind of the usual approach to tensor multiplication and this kind of somewhat newer approach or alternative approach called a padding tensor. And so the idea here is that the usual approach, so first of all, if you have a tensor network, again, this is a network with the nodes being the tensors, and then you've got the edges being the communication between them. You have to multiply those tensors together, right? Do the linear algebra on it to essentially break that down into the final answer, right? We talked about those contraction paths. So you need to do tensor multiplication. This is just like in machine learning or AI, you do a lot of matrix multiplication, you do tensor multiplications as well. If you are modeling your complex system in terms of tensors, there's a good chance that you're going to have to do the linear algebra on those tensors, and that essentially means you're going to be multiplying tensors together. So there's 2 ways you can do that. The usual approach is to use indexes, right? This index approach is to kind of just use the indices within the tensors themselves to kind of do the linear algebra and get the multiplication to happen. Another way is to use a padded tensor. And a padded tensor, like it sounds, it takes a tensor and kind of pads it with different zeros. And basically, it aligns the dimensionality between the tensors that you're multiplying. So if those dimensionalities aren't really the same, the multiplication becomes quite inefficient. It takes a lot longer. If you use this padded tensor to kind of align the dimensionality between the tensors that you're multiplying, then the linear algebra just tends to go a lot more smoothly. So they're using this padded tensor approach to get the tensor multiplication that they need to do in these tensor networks to happen more efficiently. Again, the overarching theme throughout this whole thing is to try to get classical computing to compete with quantum computing. So they've really got to optimize the different things that are happening. Tensor multiplication is a big part of that. They've got to optimize that. They've got to decide how to model the quantum circuit like we did in the last figure. Figure 2, they got to look at the space-time complexity trade-offs and understand that with respect to the tensor contractions and so forth, right? So they've got to make sure that they're kind of optimizing all the pieces. And the parallelism, the 3-tier parallelism scheme in the last figure 4 as well, right? And then we go to figure 6. And so this has to do with quantization. And quantization means you're basically just reducing the precision of your calculations. And the reason you would do that is because the less precision you have, the faster your calculation is going to go. Now, obviously, you got to be careful here. There's a trade-off. If you reduce the precision too much, then you're going to get answers that are not accurate, obviously, right? So this is something that's done. You see this in machine learning and AI as well. People will release quantized models. Quantization is, you really want to reduce kind of the memory footprint of the thing you're delivering. You want this thing to just not take up so much space, so you can reduce the amount of precision, which would reduce the amount of data that you're essentially storing to get the model or the simulation to happen. And that's called quantization. So what they're doing here in figure 6 is they're looking at the compression ratio versus the relative fidelity. So think of quantization as kind of a compression, right? If you're reducing the amount of memory that needs to hold because you're reducing the precision, then you're essentially compressing this tensor network, right? You're compressing the model. So if you do that, you're going from the original data to the newly compressed data. Well, what you want to make sure is that the newly compressed data is obviously quite similar to the original data, right? Otherwise, you've lost too much information, right? So the best compression we know would be like a lossless compression, right? Where there's no loss in information. Quantization is likely going to lose some information because you're reducing the precision. You want to make sure you don't do that too much. So what these authors are doing in this figure 6 is they're looking at what the relative fidelity is for different compression ratios. The fidelity is the difference between the newly compressed data and the original data. You want there to be a lot of fidelity there after the quantization process. Okay, so hopefully that makes sense. Quantization, reduce the precision, but make sure that we don't do it too much. Make sure that after we compress it, the fidelity is still there, meaning the compressed data still looks like the original data. And then in figure 7, they're basically doing kind of a more real-world version of that same thing. Now they're literally taking a 4T tensor network, which is a tensor network composed of 4 tensors, and they're looking at the quantization across this 4T tensor network. So again, we want to make sure the fidelity is there. And they're taking a look at the relative fidelity. They're also taking a look at the energy efficiency, and as well as the kind of the internode communication time. So again, they're looking at quantization, just like figure 6. Now they're doing it on a real 4T tensor network, and they're looking at the things that matter, which are, again, that relative fidelity, as well as the energy efficiency and the internode time of communication, if you will. So things that really matter in a realistic setting. So you can take a look at the chart there in figure 7, and that's essentially what that's communicating, just to make sure that that is still performing well after quantization. And finally, we get to figure 8, and figure 8 is kind of looking at what happens with respect to the global memory that you're using. So the overall amount of memory you use at the global level, let's say before it trickles down through the 3-tier parallelization regime. The 3-tier parallelism scheme, if you look at the global memory, then they see how that relates to the time to solution, so literally how long that calculation is going to take, and also the energy efficiency again. So, basically it's stepping back and saying, if we throw a ton of memory at this, what does that mean in terms of its efficiency and its time to solution, right? And so that's what this figure shows. And this has to be understood, again, with respect to figure 2, right? Going back there, which they said, don't forget the space-time trade-off, right? The space complexity, time complexity trade-off. Yeah, you could put a ton of global memory on it, but there's a cost to doing that. We don't have all the GPUs in the world to use, but in this example, they did use quite a few GPUs. Okay, so that's really the take-home message of this paper. I'm going to do a quick recap. I want you to understand the concepts. In these episodes, I'm not going to break down every little possible detail in all the words. I'd literally just be reading the paper to you, and then, you could obviously do that yourself. But hopefully you understand the concepts, and these are what matter. So the kind of main research technique here is if you have a very complex problem, like trying to simulate a quantum system, something that a quantum computer might normally only be able to do, you're going to have a lot of computing power there. And you're going to have to optimize a lot of these different things. You're going to have to think about the space-time trade-offs. And all the things that went through these figures are the kind of things you're going to have to optimize in order to get the classical computer to compete, okay? So I think that's a good message. Whether you're doing a simulation of a quantum system or something else that's highly complex, maybe it's an AI or whatever. So let's just do a quick recap of a lot of what these things are. Again, in figure 1, you've got that difference between the classical and the quantum computer. You've got the circles showing the classic. You've got the squares showing the quantum. You've got those hollow circles saying that there is a loophole with classical computing that if you sample incorrectly, which means it has correlations inside, it's going to artificially inflate the performance of the classical computer. And that's not going to be a fair comparison. So anyways, they make sure the comparison is fair. They show that these researchers are showing that the classical computer is, in terms of performance, outperforming the quantum computer, which in this case is Google's Sycamore quantum computer. Figure 2, they're showing the trade-off between the space and time complexity. They're trying to find something optimal. They're thinking about it in terms of the contraction paths across the tensor network. Again, that just means the different kind of linear algebra recipes that you take with those tensors to finally get the answer. There's ones that are better, and there's most of them which are not. And you can look at the time complexity distributions to help kind of narrow down the most optimal kind of region you should operate in based on the resources that you have. Figure 3, they're showing kind of a sample of a quantum circuit that would be at least somewhat similar to the Google Sycamore circuit. They talk about it in terms of the single qubit gates and the 2 qubit gates. Again, these are the operations that you do on the qubits themselves. So you got to make sure that the sequence of events that you're simulating are in line with what a quantum circuit is actually doing. In figure 4, we see the actual 3-tier parallelism scheme that the authors employ. So how do they actually break this tensor network down to get them computing on different nodes? How do they make sure that the communication between the nodes is happening effectively, that whatever communication intra or within each node is happening effectively? So really taking that hierarchical approach to break it down to make sure that they can scale this problem. In figure 5, we see the difference between the usual approach to tensor multiplication and the padded tensor. Padded tensor just allows the tensors to kind of get aligned dimensionally, and that allows the tensor multiplication, the linear algebra, to happen a lot more effectively. Again, another optimization that they need to do. Figure 6 is taking a look at the effective quantization. They're going to reduce the precision of the tensor networks, but they don't want to do it too much. And the way to kind of measure where that good spot is in terms of relative fidelity, that being the difference between the newly quantized data and the original data. You want that difference to be small, obviously. So they're taking a look at the relationship between those compression ratios, thinking of quantization as compression, and relative fidelity. And then they do that even more realistically and actually take a 4T tensor network, which is a tensor network of 4 tensors, and they take a look at the relative fidelity again through the quantization, but also take a look at the energy efficiency and things like the time, the communication time between the nodes. Okay, and then you've got, and that was figure 7. And then finally, figure 8 is just kind of a global, if you throw this much memory at the problem, what does that mean in terms of the time to solution? What does that mean in terms of energy efficiency? So that is the kind of thing you have to do if you want to get a classical computer to do something that the quantum computer is doing. Again, Google made that announcement in 2019 that it would take 10,000 plus years for a classical computer to do the same thing. And here we are in 2024, only about 5 years later. And these researchers have done it. So that's kind of the message in this paper is, I guess there's still classical supremacy as opposed to the quantum supremacy. Now, of course, that could change soon, but that's why I called my episode In Science in Perspective. Again, go check that episode out in that podcast. I'll give the link in the description. That one's called Classical Supremacy. Quantum computers are very hyped for now. They only do so much, but you can see how much computing power you actually have to throw at the problem to get the classical computer to do the same. So it kind of still is in somewhat favor of the quantum computer as well, I suppose. Okay, that's it for this episode. Until the next one, take care.